research in India and the United States. His PhD work focused on statistical techniques for extended range prediction of the Indian monsoon, and he received his PhD in statistics in 2014. Dr. Acharya is currently at the University of Colorado. It's CIRES. He's a research scientist, level 3, and works with the NOAA ESRL and Physical Sciences Laboratory. And he's actively engaged in several regional climate outlook forums and co-leads the building block 3 of Regional Information for Society for the WCRP. And his work currently also supports FEWSNET. So he's speaking with us about his work developing an experimental probabilistic forecast that can support agroclimatic outlooks for the Famine Early Warning Systems Network. And these predictions based on the Copernicus Climate Change Service, the C3S multi-system dynamical forecasts, which he further processes using a novel machine learning approach. So on behalf of all of us here at UC Santa Barbara and our remote attendees and the future watchers of this recorded presentation, thank you very much to Nachiketa for speaking with us. So please go ahead and share your work.
Thank you, Laura. Yeah, let me start with sharing my screen. So you can see my screen in full mode, right? In presentation mode?
Yes.
Okay, yeah. Thank you, Shad. Thank you, Laura, for having this opportunity, to having me for to explain our ongoing work at PSL series. So this work is actually our ongoing work, and I should also acknowledge my colleagues, Kyle Hall, Andrew Hoyle, who is the PI of FEWSNET from the PSL side, and also Maya, who is also helping us. And also Laura gave us a kind of short my introduction. I just want to tell you that I'm not a climatologist at all. I'm a theoretical statistician, but in my journey last 10-15 years, I became a climate statistician. So I'm still learning. And thanks to all my colleagues, friends, and collaborator students. So it's kind of I'm kind of exploring the road by walking the road. So yeah, if you find something, please let me know if I misinterpret anything in the climate science. So on that note, I start today's discussion. So like, what is FEWSNET? I think most of us in this discussion know, but just a little bit of a description of who are not aware of that. So it started in 1995 in response of a devastating famines in East and West Africa by USAID. So basically, it's a famine early warning system network it started with Africa. Now it's reached out so many different parts of the world, which main concern to give a early warning for the food security. And in the United States, there is like a lot of agency involved. NOAA is also part of that, and CHS and Santa Barbara system centers, NASA, USGS, USDA. So it's a kind of a collaborative project, and I'm a very new addition of this project. I started working PSL last year in April, and I started working in FEWSNET somewhere in August. So I'm still learning this FEWSNET, but I really like this system because it's helped a human at the ground level with the result of the science. So that's excellent research to operational project. And there's a paper published in BUMPS, which is on the 30 years of that. And like a lot of authors who are actually today's audience, they are part of that. So they know much better than FEWSNET than me. So I just encourage, if anybody wants to know about FEWSNET, please read this excellent paper published in BUMPS. So what we're talking today is like the seasonal outlook. So all the different information FEWSNET give, and one of them is like also the seasonal outlook for the upcoming season in terms of FEWSNET, in terms of agrometeorology system. So what I understand up to now, the FEWSNET are using different seasonal outlook from different sources, like NOAA Climate Prediction Center, C3S Copernicus Climate Center from European Union, International Research Institute, Columbia University. So they kind of using all the different forecast maps and try to make a consensus forecast. But what I understand while talking with Andy Hoyle in this project PI from PSL, that we need a standalone product which is more high resolution, is also should be calibrated because we were using a lot of climate model data. And also it will be tailored products, like not only the products for all over the globe, also like the particular product which is really needed for FEWSNET. And also it's need the focus from the extremes instead of just a three categorical focus. So on that note, I started working on this system. But as I have a background of working on seasonal forecast since 2010, I just want to give a little bit of background of how the seasonal outlook is prepared for FuseNet. It's not like suddenly we started something. So we go through all different steps and then we found which method is good. So just a little bit of idea about how the seasonal prediction models work. So it's actually divided in twofold modeling. One is statistical modeling, which is purely data driven, like you have a time series of rainfall for a particular area, and if the rainfall has auto correlation, you can just fit simple auto correlation model like ARIMA or LSTM or this kind of things. And if it is not like that, if you know the predictors, for example, ENSO is a huge predictors of the seasonal forecast, you can also use this teleconnection map to produce. So these are like statistical models. Then the question is why we go for the new dynamical modeling? Because it has a limitation. Because we know the autocorrelation of rainfall is very poor in any part of the world. And also the relationship between rainfall and the predictor is going changing on the climate change scenario. So if you have 100 years of data and you make something, fit a model, and then you try to predict in real time, it might not work because this 100 years also include like the non-stationarity of this teleconnection. So that's what people start thinking about a physical process bed modeling, which is based on dynamical modeling or general circulation modeling. And it's a quite a debate between two modeling, and now since last decades people understand that the power of dynamical modeling. But still we know like although it's based on different physical process, but it's based on a lot of assumption, so it's not exactly what we are expecting. So it also has a bias. So we need to calibrate. And also, it's not only one particular model because different centers have their different schemes to run this model. So it's at the end of the day, we need to have this multi-model system. And based on that, we need to make some kind of seasonal prediction. So that's what we are going to discuss today. Like we want to discuss about a probabilistic multimodal ensemble system where to use a machine learning. So basically, the inputs of different climate products or forecast products from different general circulation models, and we process such a way to make up probabilities. Now the question is, do you just jump like, okay, so machine learning is like a big thing right nowadays, just use any kind of machine learning, or we should start with step-by-step process? And I think that's more important because if we have a simple method, why should we go for a machine learning models? And what are the limitations before we go to the machine learning models? Because this science is like well evolved since 90s when T.N. Krishnamurti published a paper in Nature of multimodal ensemble using super ensemble, which is basically a linear regression. So why we need a machine learning now? And also, if we need a machine learning, it will be very transparent. Instead of just putting the data in a system and run for a couple of days and get something and without understanding anything. So that's what I start for this discussion to building up how it started and then why we need. So so before going to multimodal, just think about one single model. And if you have a climate model with different ensembles, how you calculate the probability? It has a different method. So basically there's two method. One is non-parametric and parametric. Non-parametric means you are not using any kind of statistical distribution assumption. So the way it calculate, suppose you have like 80 ensembles, and suppose you know the bins to predict, like or the categories to predict. So you simply count how many members falling in each categories, and you just calculate the fraction. It's called probability of like number of ensemble of each category and divided by the total number of members. And then there's a set of people who come with the parametric distribution. Generally, seasonal forecast, they assume it goes normal distribution. So just calculate the mean of the distribution and the standard and the standard deviation of the distribution, and then you have a mathematical formula, and then you can calculate the whole distribution. That's like a two different majority of idea to calculate the probability. Now suppose you have the probability from each GCM. Now how you go for the multimodal? And again, it has a two different way. Non-parametric way is like, Suppose you have this P from each GCM of GCM I, and we need to find some kind of weight function. Suppose you have 10 GCM and you have like 10 probability, and how you give the weights for the probability. So we have studied different kind of method. Start with a simple average to giving the weights based on their number of members or signal to noise ratios or correlation. So we can play with different kind of things, but at the end you find maybe one is better for one particular season, what particular region. There's no like a, a one answer like which method is work. Same as parametric, like again parametric, when you calculate the probabilities, you have to calculate the mean, which is easy because you just use the multimodel ensemble and deterministic. Like suppose you have 10 ensemble, 10 models, you just make some kind of super ensemble or average to get the mean. But what about the standard deviation? Then there's a lot of different way to calculate the standard deviation. We also studied on that, and we found like the correlation with standard deviation may works. So there's a lot of, as I said, a lot of established research already done in this science. But then why we go for new system? Because both the method has a limitation. The major limitation of non-parametric is when you have a very fewer ensemble members. Suppose you have a model which is only have 5 members, and you have to calculate the probability for, let's say, 10 categories. So it's always a challenge to calculate when you have a fewer members. In a parametric method, the major limitation is like it's a two-stage modeling. So first you have to calculate the well-calibrated deterministic forecast. Then you have to convert the deterministic forecast in probability. And for that, you need to have assumption of mostly normal distribution. But not everywhere this normal distribution assumption is actually followed, because when you think about the forecast, it will be across the season, across the calendar years. So there is a limitation of this two method, and that's what we're thinking about the next. Now, before I going to jump, I just want to tell you, like, because I'm belongs to NOAA, so what the NOAA already have the product. So one of the products, you may aware of this products called NMME based product. Every month they produce a seasonal forecast. I just pull out the one map for season one, and you can see like there's a raw probability and there's written that pack calibrated probability. And what is the pack? And if we have a pack, then why I need to do something else? So this the method called probability anomaly correlation, or PAC, and it's the paper published in 2017 by Van Doel and Emily Baker and others. So basically, it's a combination of non-parametric and parametric approach. So first, they calculate the probability from each GCM by counting the members. And once they have the probability, they start to make a fitted line between the probabilities and whether they even happen or not. So basically, in mathematical way, you can think about, you have two data time series. One is the probability, which is from 0 to 1, any value. Another one is like the actual observation, whether it's happened or not. So it's either 0 and 1. And if you think about a mathematical way, if you do the linear regression, you always ended up with this kind of regression where it's unbounded. And that's what in their paper they use appendix. They said like, yeah, so we are actually having this kind of problem. So we are kind of do a manual tuning. Whenever you have a probability greater than 1, do this, or less than 0, do this, because it's not mathematically a correct way to regress between 0 and 1 and continuous data series. The best way to do is logistic regression, because logistic regression is bounded. So it's actually, logistic regression became popular because it's used for dichotomous time series, which is 0 and 1 and continuous. So one of the option to logistic regression. Now here the point, like, okay, so logistic regression is very simple to understand. It's basically, if you have different category, you can calculate and you can fit the logistic regression for each category. But there's a limitation. Suppose you think about, you have 3 category. So that means probability of below, probability of above, and your normal. So basically you are fitting the logistic regression for each category independently. But when you sum up the results, it again have the problem with whether it's beyond 1 or less than 0, because each of the fitting doesn't have the information for the other bins. So that's what, there is a method called extended logistic regression. So in the logistic regression equation, you just add one more term, which is based on the quantiles. And then you kind of calculate the probabilities for full distribution. And this method is actually developed by Wills in 2009. And when I was in IRI in 2017, I kind of started this method, and still IRI using the same method we call ELR, or external logistic regression. In this method, we are kind of calculating probability for each NMME models, and then you simply average the probabilities uh, based on how many models we have. So the point is, when I established this thing like 5 or 6 years back, I also understand the limitation. The one of the limitation is take a longer time, because logistic regression needs iteration. And when you calculate for each grid and for each model independently, it takes forever. And also, it's not appropriate for temperature. So we also work on that. So the temperature forecast, if you look the ELR based forecast, it has some issue, because it's the probability is not strong in the tropics, it's mostly strong on the subtropics. And also the scale of the temperature forecast based on this ELR is much worse than the non-parametric method, which is not calibrated. So then we found there is a problem with that. So based on all this background, we are thinking, let's try something else. Let's try a learning which is based on the statistics and based on the machine learning. So it's a combination of machine learning and statistics, but that framework which use the statistical functional analysis. But as we talk about machine learning, we also understand the limitation. For any kind of machine learning, deep learning, we need a lot of data. And here, as you all know, like climate models have only 25 or 30 years of hindcast. So we cannot use a very sophisticated deep learning, and then we ended up with overfitting. So we have to find like which simple way and understandable way to use it. So we started this simple single hidden layer fit forward neural network. It's basically you have a different inputs and you have one output and you have one hidden layer. And suppose these inputs are different GCMs and your target is making a one forecast, and you can use that. But again, there is also a limitation. Although it's simple, but it's take a longer time to adjust the parameters, because any kind of machine learning, including neural network, has parameters and hyperparameters. Hyperparameters where you can control, like for example, how many hidden node you want, or how what is your learning rate, or what is the epoch, how many epoch you want. And all this at the same time, the way it works is actually go on working such a way that it give you a best network which has less minimum error. So it's like if you think about operational forecast type of operation forecast concept, sometimes it take a longer computational time, or like suppose you need to make a forecast tomorrow, may take longer time than tomorrow. So that's what you also cannot use this kind of simple method. So on that note, we started using a method called extreme learning machine, which is a kind of a generalized form of SLFM. So the way it works, instead of like fitting all the part of the method, all the part of the network, is started with a randomly weights and the bias in the first layer, and then it goes to the next layer, which is hidden layers and output layers, and train. It's never come back to the first layer. So that's the way it started, and this paper published in 2008. So there is basically, if you think about a math or think about a regression framework, it's look very similar to the linear regression, although it doesn't use any ordinary least square kind of things. It's used like Moore-Parson G inverse, because it start with the random weights. Suppose x1, xn is the GCMs, and you start with some kind of W's, which is weights, and B is the bias, and then it goes to the next layer, which is the hidden layer to the other layer, and it started working on looking like a linear regression, but it's used a different kind of iteration to calculate, but it's much faster than a simple neural network. So we thought about, let's use that method. And it's also very transparent, because you can see the equation, you can see the weights, and you can actually customize this network very easily. Excuse me, compared to other deep learning methods. Now, just to one example, like this method is in 2008. So we started this working this method long back in 2014, during my PhD time. And I was thinking to just to see this method, how it works in terms of just a deterministic forecast. Like suppose you are making just a deterministic forecast, and you compare it to all the standard method, which is ensemble mean or in linear regression model. And if you compare this method, how it works. And the result is very encouraging, because not only the skill score, if you look at the box plot, which actually show the spread of the data, and you plot it for observation and each different regression based mme and elm, and we found they have this elm also captured the spread of the observation, which actually encourage us to use it for probability. Excuse me. So we thought that as this method has also captured the spread, it can be used very easily for the probability. So we start with ELM to make a probability, but it's not as straightforward, because neural network is mostly is created either for the regression problem or a classification problem, and that classification is just for a binary classification. For example, cat or dog is not for multi-class. So we started working on that, and then we found there's a paper in 2019 they call probabilistic output of extreme learning machine. Excuse me, it's so dry. And we thought, okay, so if there's a method is established, then we just use this probabilistic output of extreme learning machine. But we found that in terms of seasonal forecast, we need to also think about the mutually exclusive probability. So it's not fitting different thresholds, just like a logistic regression. We should need to have the probabilities, the summation of probability of one and all the different things. So we kind of start working to modify this whole system. And also it has a log function. If you look the equation and think about when you fit the probability with the observation, whether it is 0 and 1, if you take the log 0 or log 1, it's always a problem. So we started working in different, customizing this whole thing so that it can work for the seasonal scale. So in terms of pictorial representation, so ELM is look like this. So you're just a neural network. You have inputs, you have one output, which is like deterministic. But from here, we make like three category forecasts, which is probability above, normal, and below, and using a sigmoid function at the output layer. So from this to this, with all the modification, we have some method. And the way we implement it at PSL, so we use the predictors from C3S. We can also use NMME. The reason behind using C3S of the recent papers where he found there's an excellent paper, or actually diagnostic the skill of C3S over Africa, and comparing the NMME, I found these models may be more helpful. And also to use the most recent climatology, which is from 1993. So we thought to start with this thing. And also we use the observation from this group chips, and because it's 0.25 and 0.5, so we started up to now 0.25 instead of just 5 kilometers. But as we are starting as an operational system here, so we cannot rely on a database or data library which is in a third party, for example the C3S system itself or the IRI, because what happened, as we all know, like C3S system sometime down, sometime for over the week we cannot download the data. And also it keep on changing the different version of the model. For example, the ECMWF right now it's use 5.1, whether if you go to the IRA data library, you can still, there's a 5. So we started thinking about our own database, and thanks to Kyle, my colleague, who did that hard work and make a local database. And we also making operational focused script, which is a semi-automatic. So we still like doing a babysit on the code, but the plan is in a couple of the months from now, it will be like cron job automatic. So the way it works, we already download all the hindcast data. In the operational script, it's actually started downloading the forecast data from the models and then do all the post processing and create different maps for the hindcast scale. It also create the different forecast in different leads, and not only for the seasonal forecast, it also for the monthly forecast, and then it will display it. And the plan is to have a real-time website, which is working on that with the group in PSL. Right now, we are making this thing and just sharing this maps to our PI, and Yuhel, and who is actually sharing this map to the FEWSNET every month discussion. Here I just want to show the different skill of the season, because we have like monthly in different leads. So just not to make so complicated for this talk. So these two canonical season, one is JJA and one is DJF. And this map is for generalized ROC. So ROC is a verification matrix for probability, which help us to calculate whether the probabilities is discriminant to the different categories. So that whether you are giving the probability of one event every time, or you're giving different type of probability, and how much it is better than to your hit compared to false. So for example, you're giving probability of above, and but it happened below. So that means you're false. But if you give the probability of above, it's happened above, so it's hit. So anything greater than 50%, that means when is the 50%, that means your hit and false is same. But anything greater than 50% is better, because your hit rate is always greater than the false rate. So we are kind of calculating the probabilities here. And the white here is actually the dry mask. We calculate the dry marks in real time basis. Like the condition we use that at least the 10% of the data, if it is like, or other way, like if it is 90% of the data on that season is dry, we are not calculating the probability. So we found kind of encouraging skill here, although like we know the seasonal prediction skill doesn't come from the post processing. Also, on not only it's also come from the climate models. It's also come from whether the INSO is strong or not. But whatever we get here is kind of legitimate. And then also we calculate the reliability diagram based on this whole GROC. Wherever the GROC is greater than 50%, we calculate the reliability. And it also kind of a moderate skill. It's not like perfect reliability, as you know, like getting a perfect reliability in seasonal is like impossible right now. But we kind of get a moderate skill, and then we get an confident that yes, this method can works for the real time. Based on that, we started this forecast September 2022, and this is the forecast issued in October. And three category forecast. And if you think the probability is very high for the abnormal because of the La Nina event, and we kind of compare this probability with the other available uh, maps or forecast of different center that time, and we kind of confident that yes, this probability look very reasonable, not looking very different. So that's the way we calculate. And also we calculate the skill in the real time, because as I said, like the models are changing, keep on changing their version. So we started thinking calculating the skill in a real time system. And we also very confident of this probability that time, because we see that the higher probability is also having the higher skill in the same particular region. So we are more confident to disseminate this forecast rather than having a higher forecast but having a lower skill. So we calculate kind of in a real-time scale to produce this forecast. We also create this region-wise forecast map, because in the discussion of FEWSNET every month we have region-wise discussion, and Andy Hoyle is mostly responsible for the Afghanistan, but we decided to make all the different regions, and now we are working to make more regions, like which is North American, South America, Caribbean, and globe. I just keep those real-time forecasts that time in October, where we don't have this kind of semi-automatic system. We just starting using our own, but that's kind of a real-time maps we share with our partners. Now the question is, up to now we talk about three category forecast, which is a common standard for seasonal forecast. But what about the extremes, or what about the full distribution, or what about the probability of accident of certain threshold? So right now the system we develop, which is POULM, is not producing that kind of probability. So we kind of stuck there, and then we thought about let's modify again, and let's modify such a way that this whole network gives us a full distribution. And we called this distribution called extended POLM. So instead of having the probability, now we have the whole system where you can calculate the probability of y of greater than any threshold of any time. So we are actually modified the whole system, and actually develop this whole theory, because there is no paper published yet to calculate the whole distribution. So we are working on this whole theory to make an extended version of this POLM, so that you can have the full distribution. Once we have this thing, then we thought to make the probability of different threshold, and we start with two different category. One is the highest 20th percentile and lowest 20th percentile to display, although we have the probability for every percentile and every method. So this is again the same season, the October start NDJF, and you can see the probability of the highest is always higher here in the southern Africa, and probability of below, which is less than 20th percentile, is higher in the Eastern Africa. So we also kind of experimenting this product in different threshold and different things. So now the next goal is like to make the full PDF, like full distributional graph for each grid, and so that people can also look at it, how it compared to the the earlier climatology. But that is purely based on machine learning. So it's not based on any statistical distribution, rather machine learning based the whole distribution of the forecast. On that, I just also want to tell you, like, although these things are very fascinating to listen and to thinking how to make this thing, but there is a lot of limitation of calculating those things, especially on this package. So now is like Python era, and everybody using Python, and we thought like, okay, so Python have some kind of ready-made tool so that we can work. But unfortunately, there is no tool available for this kind of things, where because most of the Python tool available for some standard data, which is like tabular data in Excel format, you can play different kind of machine learning. But think about multi-dimensional climate model data, and also having this kind of hindcast forecast. So we started developing the tool like since last 2 3 years, and now we are kind of working more and more so that we can develop this tool for FEWSNET. We call Xcast, which is a combination of Xarray. Xarray is a Python package, and the hindcast or forecast. We also implemented this chunk-wise parallelism, so that because we are calculating probability for each grid, so if you just run this thing, it take forever. So we are trying to use some parallel processing or parallel computing within this tool, so that the whole forecast and hindcast is calculating fast. And it also have a lot of different options. We just use ELM for this method, but it also have like random forest, and I can say the naive bias, the quantile random forest. So many different method is already there, because when you make the tool, it's like for general, but right now we are using also for FEWSNET, but this tool can be also used for different kind of categories and different kind of problem. So on that note, I just want to conclude my talk that as we found that the traditional way of calculating the probability from different multimodal system has their own limitation. So we start thinking about a machine learning model, which is mostly on the white box approach, so that we understand what's going on and we can modify based on our own requirement instead of just using a standard method. And based on that method, we are using this seasonal and monthly forecast, and which is going to be displayed in real time and NOAA PSL page soon. We are working on that. We established the whole system. Now we are working with our excellent group of web page developers so that it can be done quickly. And we also thinking about different drop down menu in the web page, so that different regions, different products, let's say tercile probability less than 20th percentile, highest 20th percentile, and also different skill score. I just show two of them here, reliability and zero. We also provide RPSS, CRPSS, and all those standard skills map of the probability forecast. Right now, everything is developed for the rainfall. We're also working on the temperature, and the temperature, it will be three product, like minimum temperature, maximum temperature, and mean temperature. That's what we are working right now. And also in terms of a theory, we are thinking about how to evaluate those extremes. Although we are calculating this probability of 20th percentile for lower and higher, but how to calculate the scale. The biggest problem with that, because when you have the extreme probability, that means it doesn't happen very frequent. So in terms of calculating the scale, you don't have much, like you don't have like 25 or 30 years of data. Maybe in 30 years you have like 5 or 6 cases. So thinking about a proper strategy, a proper theoretical strategy to evaluate those extremes, otherwise it will be like, again, very overfitting kind of thing. So we're thinking about that. We may use some standard method, or you can use some kind of new method. So that's what we are working on that right now. On that note, these are the reference of the papers, and I'm very open to any kind of questions and feedback and future collaboration. Thank you.
Thank you, Nachiketa. I wonder if Laura may be having some internet issue again. Just so everyone, please feel free to ask any questions you may have. This was a very interesting presentation, and I really liked that Nachiketa took time to explain us the methods, going from the linear regression. Sorry, one second. Come in. Sure, please. Go ahead. Let me just change this. Let's see. All right,
Okay.
Laura is here now.
Hi, thanks so much for that presentation. I appreciate how you went through all the different steps that you got at each point of analysis and clearly identified the limitations and really the decisions that any of us would need to make at each point in time, like the difficulty with the small number of models and the different hindcast periods that each of them provide. And so I have a question, sort of a summary question to start. So my understanding is that really the gain that this additional processing is giving us is that it transforms the derivation of the probabilistic forecasts so that it's just done in a more appropriate way, given all of those limitations. Is that correct?
Yes.
Okay, I can't hear him. And so when you put these, when you make these available to us to look at, as you mentioned, the skill is mainly, well, it may be mainly coming just from the climate models themselves. And that skill is really hinged upon ENSO predictability and ENSO being active. And I noticed that in some of your ROC maps showing the high skill in Northern Ethiopia and in Zimbabwe as well. So is part of your process going to be to show us how much better the skill is in these forecasts versus the raw climate model outputs? Or is that not part of the goal here?
Now, Laura, thank you very much. It's actually part of the goal. So right now we are working on the paper. So the way I have planned that paper, I start with the non-parametric counting members, where non-calibrated forecast, you just have the members, you calculate the probability. Then the skill of the pack method, because obviously I have to cross the CPC pack, otherwise NOAA cannot take this method. And then which I have developed for IRI, which is ELR. So the section of the paper will be like comparison of different things. We have this initial result already, but the reason I don't want to show here, because first of all, I don't want to like show that, oh, the machine learning is the magic and you see the skill everywhere. It's not like that. That's what I don't want to show, although I have a very encouraging results. And when I say the results, right now I have 1 or 2 season. I want to do like a all lead 1, all lead 2, all lead 3, like repeatedly. For example, January start, February start, March start, instead of just 1, 2, 3 season to show. But
Yeah.
still we are working on that. So the part of the script we are making right now, all this for the operational forecast, where it's also calculate all the skill for all the season. So that's what we're kind of taking a break instead of just looking at different season, rather run the whole script, make all the plot, and then we can calculate those scales. So yeah, so that's the plan. Otherwise, as I said, otherwise there's no point to use your GPU time or computer time if the simple method works. Yes, that's the plan. Thank you.
Okay, very good. And my question was, going forward, you said you were looking at temperature forecasts as well. I wondered if you had considered looking at the joint probability of precipitation and temperature, such as the probability of a season that has below average precipitation and above average temperature, or even getting into more of the extremes.
Again, very excellent question. So the reason I take a little, I can say like pause before I start working on temperature is different in many folds. So one of the thing is like, although we thought like temperature is more predictable because it's continuous, you can just fit a normal distribution, this and that. But one thing we always ignore in seasonal prediction, which is the trend. All these 30 years. But if you just calculate the trend of our temperature data from the observation and do the same thing for any kind of modeling system, whether it is NMME or C3S, you can see very different trends, especially over the Africa. That's what I experienced with. So I was thinking to use a calibration method which also include the trend. And in CPC, there's a group called Dan Collins and Jonah Infanti. They are using a method called Bayesian joint probability with the detraining methods, where they are actually trying to use that the actual trend from the observation and actual trend from the climate model and try to include them instead of detrending and do the calibration. So that's one of my plan instead of just doing this extreme learning machine things way. Coming to the joint probability of rainfall and temperature, that's also an excellent question. So the plan is right now, once we have this whole rainfall and temperature independently, our plan is to calculate the, the drought index like SPEI, where you can actually combine these two. Instead of two different joint distribution, you can just calculate this SPEI so that you can have the thing. So one of my partner in the CG from the CIMIT, Mexico, they have a project on South Africa on that. So I kind of collaborate with him and try to develop our tool so that it calculates the SPEI. Now the question is, I don't want to go on that, but the question is, in which part you calibrate it? You start with the calibrated temperature and rainfall independently and then calculate SPEI, or you calculate the SPEI from the climate model first and then you calibrate. So we are kind of like, that's what I believe on solving all those doubt rather jumping directly to the thing. So taking little time and thinking about what will be the best way to do that. But that's an excellent question. Thank you.
Great, thanks.
I see a hand raised. Greg.
Yeah. Yeah, thanks. I think I want to echo Laura's comments on what a nice talk you gave and walking us through the various steps. I thought that was really good. And I think her question at the end highlighted, and maybe without discussing the full outcome or results of your investigations into the value, say, of this machine learning approach versus the standard approach, are there typical, or are there regimes where you've noticed that that the dynamic models do well, or that there, I guess, maybe let me ask it a different way, where your approach actually has a real notable improvement over the standard dynamic models? Are there certain, does it work very well, say, in humid areas or mid-latitudes, or have you identified any kind of regimes, or do you think it's a little more, let's say, random than that?
Okay, now that's a good one. The whole purpose to use this machine learning or statistical learning is like post-process or calibrate the climate model. So the first goal is like, as you know, the climate model has some systematic bias. So at least this post-processing, whether it's just a statistical or machine learning, should be better compared to the climatology in terms, because you try to reduce the systematic error, and that can be easily done for any kind of statistical model. Now, when I call the systematic bias, it can be a measure of means absolute error or RMSE. But we're interested on more on the fluctuation or the signal, and that's what we're looking at, correlation, or looking at GROC kind of things. And now the question is whether our post processing is improving everywhere in the season, in the region, or everywhere in the season. That's the question. And what we found, that most of the cases, and as Laura said, like, I'm going to present this thing in the paper, like most of the cases, this calibrated forecast is always better than the uncalibrated forecast, which is you're not giving any information of the past history. But obviously there is a reasons. For example, we found the South Africa have the more scale, because we know the teleconnection of South Africa and ENSO is always high. So we got these higher RPSs, higher GROC there. but not as good as Afghanistan, or not as good as Pakistan, or Central India, because we know this teleconnection in the model is not appropriate compared to the observation. So yes, it does have some regions where the skill is good, but the skill is coming combined with the teleconnections, the seasonal dynamics, and also the post-processing. So uh, I cannot decompose like where this thing comes because of machine learning or because of this. Is kind of a combining of all those things. But yes, obviously they have different regions where you can get more skill, versus there is a reason there's we can get at least the skill compared to climatology, not worse than climatology.
Great, thank you.
Jim here. I'm sorry, I don't see how to raise my hand in Zoom. I mean,
You have
thank
a
you for a great presentation. Very, very informative. With regard to your comments on the SPEI, I guess one suggestion I have is, as you weigh your options for calculation of the E term, the event translation term, I would just suggest you have a conversation with our colleague Mike Hobbins there at FEWSNET, since he's sort of been swimming deep in that sea for quite a few years. So I think he likely have some helpful advice for you.
obviously, yeah, exactly. Like, in fact, Mike is my supervisor. So yeah.
So you had no choice, I guess.
Yeah. So in fact, recently, like when I was designing the paper, I was looking for a paper, and then I found your paper with Mike's, where you kind of develop this diagnostic of evapotranspiration from this FEWSNET area. And I have like a small discussion with Andy about that. And obviously, like when the SPI things come, Mike will be in charge of giving me his feedback. Yeah, thanks for that. And I see, Strad, you have two questions on the chat. I may try to answer that two question.
Good, thank you.
Yeah, the first one is like, is this approach robust enough to apply seasonal versus subseasonal focus? Noting that the subseasonal, especially in MMB surveys, only goes back 1999. Okay, so obviously, like for the seasonal, we use C3S, and there is a reason behind that, because it goes only 1993. It's not 1982, and the reason here that, at least for me to use the recent climate, which is now defined from the 1999, and we established this method is quite robust, and that's what we calculate this GROC and these things. So it's not random hit, rather it has something, and wherever you expect the skill, you get the skill. It's not that, oh, the skill is excellent in Afghanistan but lower in the South Africa. So it's kind of robust on that way. Now coming to the sub-seasonal, and here is the thing, as we discussed a couple of months back, I also part of a project at PSL where you work on California water system, and we work on this actually as sub-seasonal focused. So we took the different approach. Although it's a machine learning approach, we use a kind of multi-member system there. So right now we're using GFS and ECMWF. And instead of just using ensemble mean, we are using all the members in ECMWF and using sort of same kind of extended learning machine. But it has a different implementation methods rather than this multimodal system. We have tested different scale there, and up to now things are moderate. Not again, after week 3, getting a scale is not so easy. All this ECMWF. So we are using, but not the exactly same way, in a different implementation method. Maybe some part we can discuss that thing, like our scale, and it's already being used on this method, on this project, which is Julian Diaz is the PI from the PSL side, and we are working on that. Now the second question, how do you go for correcting focus probability to high resolution calibrated focus to drive impact model? That's a very good question. So you're thinking about how to use this seasonal focus to an impact model like crop model or hydrological model, right?
Exactly. Yes.
Exactly. Yeah. So that also need additional steps. The additional steps is this probabilities is coming as like one value for whole season, right? And for the hydrology model or crop model, you need a daily time series.
Mm-hmm.
So again, in a different project, with the PSL. It's called BIL project, BIL, which is a part of, like, my role in the project is actually improving this whole MEFP system in national. It's called HEFS, Hydrological Ensemble Forecast System. So, NOAA has a hydrological ensemble forecast system for all the reservoir in the US, and they are mostly running for hourly to decade or hourly to yearly scale. So where we are developing a system, like once you have this seasonal forecast, we stochastically disaggregate this probability in daily time series so that they can run. So all this is a different project, but it's kind of very connecting with this. So on that, we are right now, I'm developing a method called I give the name called WGN, which is a multi-site weather generator based on general adversarial network, which is again a deep learning method where you can, without using any statistical distribution, you can actually disaggregate those data in a daily time series so that you can run the impact model. Yeah, it's also going on, but thanks for mentioning this thing.
Great. Thank you, Nachiketa. Are there any other questions for Nachiketa? Do you have any questions? If not, I have one.
No, I'm good.
Okay. Nachiketa, just this is a general question that we like to ask to all of our early career webinar presenter. And the goal being that these webinars, one of the goal is to provide an opportunity for graduate students and early career researchers affiliated with Climate Hazard Center to learn from presenters like you. So the general question is that, say, when you come across a research question, a research problem, in this case, perhaps the problem might be to improve the skill of seasonal forecast. How do you go about identifying the most appropriate method, data sets, and designing a research plan to address that questions? In general, what is your approach for that?
Great, sir. Actually, that I already answered that question because part of my presentation start with that. Like, what are the method available already? And like I'm a big fan of reading a papers. So the first thing first, I start with reading the papers and what is available method up to now. And instead of proposing a new method, I try to understand like why people using different method and what are the limitation of the method first. And if a method is already established, I'm very open to learn that method rather putting my own method. But the point is, sometimes what happened in the papers, like especially on the climate papers or in our field, it's not very clear how those method is implemented. And when you start working on the method, then you understand the limitations. So
Yeah.
that, oh, okay, so you know what, I cannot use this method for temperature, but it works for rainfall. So I think like this is part of the process. Like start the reading the papers, try to adapt the method, and try to understand the limitation because very less paper telling what is the limitation of their model.
Yeah.
So it's kind of my model is the best model kind of things. So obviously like start the reading paper, try to code those method and get your own perspective on the method and try to document the limitation. That's important. It's not like, oh, this method is not working, that means my paper is not publishing. It's not like that. Explain the problem of the method and then try to improve the method. For example, when I read this back method and I was like, oh, that's great, they have like excellent reliability. Then when I look at the equation, then I understand mathematically it might not be the best way to do it because it's dichotomous and the continuous. So my point is like when you read the paper, also open your mind. Don't just blindly follow the paper. Try to use your own training, whether you're from maths or stats or physics or computer. Use your own training to see an independent look on the method and then you change. Not every time you are ended up with your method is best, but at least while you're doing this exercise, you kind of put your finger in the dirt. You know where it is where the problem, and it's okay. It's a learning process. If you are not ended up with the results, but at least you know the process, and which help you a lot as an early career scientist
Mhm.
When you go to the postdoc, you don't have much time. And
Yeah.
all your training in the PhD time, building this, putting your hand in the dirt is so helpful to be a smart researcher later of your life. And that's what we are all doing because we are dealing with so many different projects. We don't have much time, right? So I think like that, I kind of use my own way, my strategy. I think that may be a good model to follow.
But definitely. But thank you so much, Nachiketa. So I know we're, yeah, do you have any other comments or questions?
No, I don't. I think you did an excellent job, and we're so lucky to have had you speak with us today.
Yeah.
Thank you.
Sure. Laura, I will love to catch up with you later because you mentioned that you work on NMME and seasonal. So maybe I can just shoot an email to you and then we can discuss later about our own work.
Yes, that sounds great.
Okay. Thank you, Shad. Thanks,
Good.
everyone.
Thank you so much.
listening.
Thank you, everyone.
Yeah,
Thanks
thank you very
much.
much.
Thank you very much.
Yeah. Bye-bye.
Yeah,
very
it was
good.
great.
Bye-bye.